Okay, so let's calculate the inertia first here. So it's the inertia of the disk, which is a half m r squared, plus the inertia of the point, which would be m r squared as well. So let's type that in on the calculator. It's 3 over 25, isn't it? Because that's 2 and a 1 is a 3 over 25i. Now let's get the height here. So that's 0.2, and then that's 0.2 cos 60. So that in total is 0.3 meters. So this disk here is uniform, and its potential energy doesn't really enter the question because its center of gravity is staying fixed. So there's no point in even considering it. We'll just have to look at the potential energy of the point. So its potential energy is mgh. And then initially the kinetic energy, so to speak, due to the rotation of the system, that's 0 because it's not rotating initially. And then later it'll equal the potential energy again later, but when this gets to the bottom, its potential energy is 0. And then including the rotational energy, which is a half I omega squared. Oh, I wrote I there, sorry. That should have been M. A half I omega squared. Okay, let's cancel. 3's cancel. 5 goes in there twice. 5 goes in there 5 times. The 2's cancel. So it looks like I get omega is root 5. Root 5. Oh, let's not forget the g. Root 5g. What is that? That is 7. Nearly exactly 7, funny enough. 7 radians a second. Okay, but now the next part is find the angular displacement of the particle when the angular velocity of the disk is 5 radians a second. So find where this mass is located basically in its rotation to get a result of 5. So again, perhaps we can still use the energy. The energy at the beginning is still the mg 3 over 10. And then the energy later would be a half I omega squared, which we know this time, so that'll be 25. Plus we don't know the potential energy, mgh. So we could solve this for h, I think. Cancel out the m's. Well, that's nice. Cancel the 25s. So I get 3g over 10 equals 3 over 2 plus gh. Let's see what I get here. I can solve that and I get h is 481 over 3270, which is roughly equal to 0.147 meters. So for the first time, okay, so that would be like this, 0.14 height would be like at some point here. Let me exaggerate it a bit more. Some point like here. So we know this length here So what would be this length? So if I just draw the triangle, I want this angle here. That length would be 0.2 minus that number. So that is 0.0529, and this is 0.2. So we'll call that theta. So theta would be cos inverse. So that's 74.66 degrees. So that means the answer is this angle here. So that's 180 minus that. So that is at 105.34 degrees. Yeah. That looks okay. Seems like a sensible answer. I think this is right. Let me have a check here something. Just want to make sure that disc isn't falling or anything. Uniform disc mass for M, radius 20 is free to turn about horizontally through the center is perpendicular to the plane. A particle of mass m is attached to the edge of the disc. The motion starts in a position in which the radius of the position makes angle 60. Find the angular velocity of the disc when the particle is at its lowest point. Find the angular displacement of the particle. Oh, now actually I wonder. So an angular displacement from where it began, one would imagine. So now I feel like I should subtract 60 from the answer. Oh, okay. So I should say as my answer 45.34 degrees clockwise. That's how much it's been displaced. It's been displaced. Angular displacement is 45 degrees from where it started. And at this position here, it will have an angular velocity of 5 radians a second. So I wonder if they did that on purpose. I wonder if that was just to see who was fully concentrating. Okay, I think this question's okay. But again, I haven't done a question like this for like 2 years. So I might be a little bit rusty. Let me know if you spot a mistake.